Hello, this is Mr. Craig, and I want to talk about the Kinetics review sheet, day 105. I'm only going to talk about a couple of questions on here, mainly targeting the concepts here. Alright, the first question definitely want to talk about because we have a situation here where concentration of B has the same concentrations for experiment 1 and 2, but A does not have the same concentration. And when this type of question was first posed to my students, a couple of them started freaking out because they were so accustomed to having alike concentrations for both of the reactants, and it's okay because we have the alike concentrations for at least one of the reactants, so we can find the order for the other. Now, finding the order for the other is pretty paramount and pretty important because we want to make sure that we can find, once we find that order, then we can find the order for the other. Alright, so the first part wants to know, what is the rate law? Well, it's going to take a few steps for us to actually determine the rate law, but here's our generic rate law, where we have the rate is equal to the constant times the concentration of A at some order times the concentration of B at some order. So, probably the best place to start is by working with experiment 1 and 2. Now, again, it does not matter if you want to put experiment 2 over experiment 1, just be consistent. I think for the purposes that I've been using in class, I've been trying to put the faster rate on top, but it doesn't have to be that way. The orders will still work out for us. So what we want to do is actually place, in this case I went experiment 2 over experiment 1, and in this case here I didn't show the crossing out of the like concentrations, but actually, let me do that real quick here. Let me pull that up here, so give me a second. I'm going to start drawing on this. Okay, so since we have alike concentrations, what I want to do is I want to cancel these guys out and those out. So now that I'm left with, I have my ratio for the rates is equal to 2, and then my concentrations for A is actually 0.2 and over 0.1, which is equal to 2. So now I have this scenario where 2 to the m power is equal to 2, and again, remember, our reactants may only have an order of 0, 1, or 2. And make sure you know that what each of those orders represent. So if it's a 0 order reactant, if I increase the concentration or even decrease the concentration, the rate of the reaction will not change. Again, that's for a 0 order reactant. If I have a first order reactant, if I double the concentration for the reactant, then the rate should double. So it's equal. So if I double the concentration, it doubles. If I triple it, it goes 3 times faster. If I quadruple the concentration, then it'll go 4 times faster. In this scenario here, where we have our m is equal to 2, what is happening is, as I double the concentration, I'm sorry, this is a first order. In a second order reactant, if I double the concentration, then it's exponential. That means it'll go 4 times faster. If I triple the concentration, it should go 9 times faster. So our first reactant, actually A, has a first order. So if I double the concentration, which I did, I went from 0.2 to 0.1, so that's twice the concentration, which means that the rate should double as well, if it is a first order reactant, and it is. Alright, looking at the next part, well, now that we know that A is a first order reactant, we need to solve for B. We do not want to use the same experiments 1 and 2, so we want to go either 3 and 2 or 3 and 1. Your choice. Does not matter. So, it looks like I went with, actually let me clear that off here. Okay, so, looks like I went with experiment 3 over experiment 1. So again, I'm taking my rates and I'm dividing them by each other to get a ratio here. And then my concentrations, since I know I have a first order reactant, I want to make sure that I actually include that order. So if it is a second order, then I get to square these. If it's 0 order, then these go to 1. Doesn't matter what the concentration is, it'll go to 1. But this is first order, so what I need to do is, since I don't have alike concentrations, I need to get this information out of here and actually find out what those values are divided by each other and move them below my ratio here. My constants don't change, so I can cancel those out at least. So when I take 0.092 divided by 0.1, I get 0.01 or 0.92. I want to move that over to the same side. Move this up a little bit. So I have 6.092 divided by 0.92, and that equals 6.622. So now the only thing I have left is my concentrations that I need to solve for the ratio, or for the order for. So take those two values, divide by each other, and I get around 2.573. It is equal to my ratio of my rates. So again, don't freak out and go, whoa, what is that? Again, your only possibilities for n in this case are 0, 1, and 2. So if this were a 0 order, that would have to be a 1. If this were a first order, that would have to be 2.573. Since it's second order, type it in on your calculator. Find out what the square, you want to square 2.573. It will equal that. So that means that we actually have n as our second order. Okay, so we have our rate law, which now states that A is a first order reactant, and I didn't put a 1 there, but if you need to put a 1 there, that's okay. B is second order. So there's our rate law. There. Actually, that was pretty sloppy. Sorry about that. Part B, what is the value for the rate constant? So to calculate the value for the rate constant, we need to rearrange our variables here so that I can solve for the K. So I'm going to bring these guys over. Okay, swing them on down, just like we normally do. And then what I did was I picked data from one of the rows. It doesn't matter which one. It looks like I picked it from row 3 here. Okay, so once I picked it from row 3, do the calculation. Now, what's really important here is we want to make sure that our units are correct. Since B is a second order reactant, I actually have molarity squared here times molarity, so that gives me molarity cubed. So what I really have is molarity over molarity cubed seconds. And to get the molarity to the -2, I cancel one of those out. So now I have molarity squared seconds all under 1. Okay, so that's what this is. And again, be careful with your units. Be very, very careful with your units. All right, I'm going to skip question 2 because you guys, in my opinion, I think you guys are doing a nice job with this. However, let me say one thing. When it says percent complete, that's how much has been used. This value on top, which I don't have a subscript T, is how much remains. Do not get trapped by putting that value in for the top number. Don't do it. Make sure you're reading the question carefully. Don't fall for that trap. I know that's why College Board does that, because they want you to put that value in there. Alright, let's scan on down. Question number 5. Very good. Past AP exam question. It says an environmental concern is depletion of ozone, O3, in the Earth's upper atmosphere, where ozone is normally at equilibrium with oxygen gas, O2, and oxygen that is not diatomic. A proposed mechanism for the depletion of ozone in the upper atmosphere was shown below. You're given a 2-step reaction mechanism. Part A asks you to write a balanced equation for the overall reaction represented in step 1 and step 2. For calculating the overall reaction, we wish to cancel out all alike terms. So chlorine goes away. ClO goes away. Anything that appears on both sides of the arrow should be eliminated. Alright, so we're left with where we have ozone plus an oxygen atom yields 2 oxygen molecules. We have 4 atoms of oxygen on the left, 4 on the right. Okay? Alright. Now, the next part asks, Part B, clearly identify the catalyst in the reaction mechanism above. Justify your answer. Now, be sure that you can identify the reactants of a reaction, the products of a reaction, the intermediates of a reaction, and if there is a catalyst, which it looks like there is in this equation or this problem, make sure that you can identify the catalyst. Reactants are the things you start with. So it's on the left side of the arrow. So reactants only appear on the left side of the arrow. Products are things that only appear on the right side of the arrow. So products appear over here, reactants appear over here. Intermediates are things that are produced and later return as a reactant. Okay? So something that is produced and later returns as a reactant is considered to be an intermediate. This question is asking for you to identify the catalyst. A catalyst by definition, is something that helps speed up the rate of reaction. Well, when I look at this equation, I can't tell if it's speeding up the rate of reaction. A catalyst also helps to organize. Well, by looking at this balanced equation, I can't really tell if it's helping to organize anything. And then the last thing is that a catalyst is not consumed. So if I put, say, 10 grams of magnesium into a reaction, I better get 10 grams of magnesium back if it's acting as a catalyst. So what I want to do is I want to scan things that I start with, and typically it'll be earlier in the equation. So I have ozone. Well, I don't have ozone again, but I do have chlorine that shows up and reappears. So chlorine actually morphs with the oxygen, okay, and that's okay. That's typically what catalysts do. They'll react temporarily and form a new substance, and then it'll help the other reactants to combine with that to produce something brand new. So in this question, the chlorine is a catalyst because it's something we start with, it's a reactant, and later returns as a product. Alright, I already talked about the intermediates. So again, intermediates are things that are produced and later used as a reactant. Okay, so the CLO in this case is our intermediate. So CLO is our intermediate for the reaction. And there's only one intermediate in this problem. The overall order for the reaction, again, what we need to do is, first of all, hopefully, oh, here it is. So we're given a rate law. Okay. So since we know the rate law, we know that ozone is first order. We know that chlorine is first order. Now, you might be saying to yourself, now wait a minute, I thought you just told me that chlorine acts like a catalyst. Again, when we determine the rate law, we want to include all of the reactants up to and including the slow step. So in this first step, these are reactants. Okay? These are reactants. Now, if the second step is a slow step, we will not include the CLO, but we would include the oxygen. Okay? That's if this were the slow step. Now, I think the question's wanting us to see if this is the slow step. Don't know if it is or not. Okay, so let's go back and see. So since we're given the rate law, it wants you to determine the overall reaction order. So we know that that's first order and that's first order. So to find the reaction order, add up all the orders of the reactants. First. So our total reaction order is 2. Okay, well they didn't ask for. Never mind. The appropriate units for the rate constant, again, rate is molarity per unit of time. So it's molarity over time. Love my handwriting on this. And then we have first order here. So that means that we have molarity squared on the bottom. So one of those molarities goes away. So we're left with 1 over molarity time. And that's what we have here. Okay. Alright, the rate determining step, here we go. Rate determining step. So based on our rate law here, okay, ozone and chlorine show up in the rate law, but oxygen is not present. So our slow step must be the first step. If the rate law included oxygen at a first order, and I'm talking oxygen, the atom, as a first order, because again, we're not going to include the CLO since it's an intermediate, because we want to include all the reactants up to including the slow step minus the intermediates. Since the oxygen atom does not appear in the rate law, the first step must be the rate determining step. That looks like that's all the questions. I hope this has helped, and good luck on the test, guys.